All right, today and Wednesday, and we're done. Do you know that? 2 more sections of new material. Yeah. So today we're looking to take a look at section 12.4, which is tangent vectors and normal vectors. And there's a couple places where I'm going to give a little bit of background as to why we're creating something that's a little different than we've created before. So here's the first one. So in designing roads, this is a specific example, but in designing roads, you would want to avoid curves that are too sharp. And when we think two-dimensionally, we have a way to sort of deal with this. We talk about smooth curves as having derivatives, and if they don't have a derivative there, it's because there's a sharp turn or a couple other possibilities. But we have sort of derivatives as our way of dealing with this idea of a sharp turn. But when we're dealing with a three-dimensional surface, it becomes a little bit more complicated. So in this section and the next, in this section and 12.5. We will develop a measure of how much a curve is twisting or turning at a point. Okay, so this is, we're not developing it, we're just developing the background of it in this section, and we'll get to the actual, it's called curvature in section 12.5. And the first thing that we need to talk about is what's called a unit tangent vector. It's exactly what it sounds like. It's a tangent, right? You guys know what tangents are. This is calculus. And it's of unit length, okay? So the unit tangent vector is called capital T of t, and it is the derivative of your position equation. Your book is using r of t, divided by the magnitude of the derivative, hence making it a unit length. Okay, I have enough space to start, but I'm not going to be able to finish on the screen, so I'm just going to switch right now, okay? So we're going to take a look at how this works. We're going to do 2 things. Part A is we're going to find the unit tangent vector. And we've already given a equation, I guess, on how to do that. The second thing comes from something else we've done before earlier, combining with this, is we're going to find a set of parametric equations for the line tangent. To the curve at the point I don't want to use the word given. I'm trying to describe how to do this. My word's better. The point for the given t value. We'll say it that way. So r of t is 3 cosine t, 2 sine t, and we're going to do this at the t value of pi over 4. So just because it'll make it a little bit easier later, some of the questions that you have are going to start out much like this one did, but without the part B. And I've kind of tried to merge 2 questions into one, which is why it feels a little awkward in my description at the top. But others of the questions that you're going to deal with are going to actually give you the point. There's nothing specific or special about how to find the point. It's just the evaluation of r of t. So if I were to evaluate r of t, I will actually get a point. I didn't mean r of t, I meant r of pi over 4. The point that it's referencing here. So if I evaluate this at r of pi over 4, I get a vector, of course. The vector would be 3 cosine pi over 4. And then, and then 2 sine pi over 4. So the corresponding vector for this, 3 square root 2 over 2, Ethan mentioned, and then what would the second piece be? Yeah, square root 2. So this vector would be the ending point that it's talking about, okay? So this is indicated, this is the point that we're referencing. The point then would be 3 square root 2 over 2 and square root 2. Okay, so we'll use that value later. Let's go back to the first part of the directions, though, for part A. Part A asks us to find the unit tangent vector. Okay, so over here, our unit tangent vector is involves us finding the derivative of our vector itself. So what is r prime of t here?
Negative 3 sine t and 2 cosine t.
Okay, everybody good with that? Yeah? Okay. And we're going to evaluate that at pi over 4. So we have negative 3 sine pi over 4, 2 cosine pi over 4. What will that give us? Negative 3 square root 2 over 2 and square root 2. Very similar to the ordered pair because sine and cosine have a cyclic nature to it, of course. And because pi over 4 is a very nice value since they're matching. That's pretty friendly. All right, and so in order to find the unit tangent vector, I would also need to know the magnitude of this vector r. I guess I've left off all my vector hats. They're in my notes, but not in here. All right, there we go. And we're evaluating this. Okay, so we'd have the square root of negative 3 square root 2 over 2 squared plus the square root of 2 squared. Can anybody clean that up for me and tell me what you're going to get underneath your radical? What'd you get? Yep, 13 over 2 is it. Good job. And then if I were to rationalize it, I would have square root 26 over 2. Is everybody good with that? All right. All right, so we're ready to find our unit tangent vector. T of pi over 4. So t of pi over 4, t of yeah, t of pi over 4 would be the vector I started with up here. Negative 3 square root 2 over 2 square root 2.
Are you sure it's 13 over 2? Because 3 squared is 9.
Mhm.
Oh, wait. Oh, 4.
Yeah, times the 2. And the 2 will cancel with the 2 in the denominator. So you should get 9/4 out of this piece. And 2 out of this piece. Yeah, are we good? Okay, and then we're dividing by the square root of 26 over 2. Fun with fractions and radicals all at the same time. What do you guys get? Maybe we should do a little bit of the scene cleaning up together because I'm getting a lot of vacant stairs. Let's see, I have negative 3 square root 2 over 2 times 2 over square root 26. And then I have square root 2 times 2 over square root 26. I didn't actually write these details out on my notes, so we'll see if I can get them right on the spot. This is going to give me a 13 down here. That orange, the yellow is terrible. Let me use a different color. So I think I have negative 3 over square root 13. Does that look right to you guys? Negative 3 over square root 13. We'll rationalize in a sec. And on the other one, whoops. I have another square root 13, don't I? 2 over square root 13. So negative 3 square root 13 over 13. Square root 2 square root 13 over 13. Okay? Okay, good. That's what I have in my notes too. Always a good thing. All right, I thought I would have enough space on one screen to do the other part of this. Doesn't look like I'm going to. So the other part of this, part B, said to find a set of parametric equations for the line. And as we take a look at this, we actually have our point here. That's why we found it earlier. And we have our slope right here. So this is going to be the slope, we'll call it A and B, of the line. So maybe we have space on this screen if we know, maybe I'll be able to shrink it down if I don't. So x equals x1 plus a t, and y will equal y1 plus bt. So the a and the b are the slope from here. And then the x1 and the y1 are my point from here. Okay? We've done this a while ago. It has actually been quite a while ago, though. So that's where we're going to get these from. So my equation for x would be 3 square root 2 over 2 minus 3 square root 13 over 13 t. And y would be square root 2 plus 2 square root 13 over 13 t. And we keep using t. There's nothing special about t, so if it bothers you to have the same t here, your book actually switches the notation and uses s's at this point just to not think that they're the same as the parameter t that we used before. So if we wanted to be consistent with your book, we could actually do that too, and we would use s in all these locations as our different parameter.
Why is this not the same T that we've used before?
Such a good question, Hannah. I don't remember, honestly. I could look it up for us and we'll figure it out. Yeah. This is for some parameter S. Yeah, let me get back to you on that, okay? All right, so we're finding tangent vectors and we're finding normal vectors. And what do you remember about the word normal? About perpendicular ideas, right? So far, we have written all our vectors in terms of the standard unit vectors I, J, K. Agreed? Yeah, that's how we've done it. Sometimes, however, other choices are more convenient. For example, for an aircraft in flight, a better frame of reference will be one that moves with the aircraft. So the principal unit normal vector N of t is the unit vector having the same direction as t prime of t and is defined by N of t is t prime of t over the magnitude of t prime of t. Provided, of course, that t prime of t is not equal to the zero vector.
Question.
Yes.
So you writing that, you're saying that in normal vector of t prime, not the prime of the normal vector. You read it that way with the prime inside the parentheses.
Say that again.
Sorry. So we've written in underneath the same direction you have it in the normal vector and then you have parentheses t prime. Is that
Capital T prime, yes. Okay, go ahead. Uh-huh.
that capital? That's
Yeah,
capital T?
that's a capital T prime of the lowercase t. So the lower, this is terrible because they keep using the same letters, of course. Wish they were using S. Like that. So we've got capital T as your tangent normal vector, or tangent vector that we just talked about, or tangent unit vector. And then we've got the derivative of that.
Okay, so off to the left, on the left side, the equal sign, is that differently notated than taking the prime of a normal vector, like the normal vector?
Yes.
Okay.
This is not the derivative of the normal vector. This is just the normal vector.
Just-
Wait,
Right.
What?
Wait, what?
You said the big T prime, the big T isn't the normal vector?
No, this is the normal vector. I think what Bryson was asking was whether or not we were taking the derivative of the normal vector. Is that what you're asking me? And the answer is no. We're finding the normal
So this
vector.
is
Our normal vector
derivative-
is the derivative
T
of the
prime T is
tangent.
Derivative of the unit tangent.
Yes, the derivative of the unit tangent vector and then made into a unit vector itself.
Okay.
Yes,
So the derivative of the unit vector might not be unit vector.
correct. It wouldn't have to be. Yep. Yeah. And if you think about it, that happens, like, especially if you're talking about, like, think about what happens when you take derivatives of sines and cosines when they have multiple angles on the inside, right? You end up making constant multipliers, and so you wouldn't necessarily have to have a unit vector when you're done. Yeah. Okay. Let's take a look at an example. We're going to find the unit tangent and principal unit normal vectors at the given point. And our equation, I don't know why I was super into trig, but I was apparently into trig when I was doing this lesson. 2 cosine t, 3 sine t.
Use that R hat.
Yes, let me put that in there, thank you. And we're going to do this at t equal 0. Okay, what would we do first? So we're trying to find capital T of t and the capital N of t. Both of those two things are what we're trying to find. So what do we do first? A derivative, right. So I need the derivative. I need r prime of t. So what's the derivative of 2 cosine t, 3 sine t? Did everybody get too excited at once? Good. Negative 2 sine t. What was the other piece, Bryson? 3 cosine t. Excellent. And then if I wanted to do this in general for a generalized t, we'll evaluate in a little bit. We could find the magnitude, right? And we would do that as follows. So I have 4 sine squared t plus 9 cosine squared t. There's an identity that you know that could be useful, but not completely and totally useful.
So it'd be 4 plus 5 cosine squared.
Right. So I could take 4 of the sine squareds and 4 of the cosine squareds and add them together and get 4, right? So basically, if I were to split this one apart into 4 cosine squared t and combine it with the other one, right? So the one I had, yeah. And I'd have 5 cosine squared t left. So another cleaner way to write this, simpler, would be, this is 4 plus 5 cosine squared. Okay, ready to go with that? Okay, so if I were to find then capital T, not prime, capital T of T, right? Last time I found capital T of the point T that I was given, and I'll do that in a second, but I want to find it in general for this one in case you wanted to see that difference here. We would take the vector that we found up here and divide it by this magnitude. So we would have negative 2 sine t over the square root of 4 plus 5 cosine squared t. And then 3 cosine t over the square root of 4 plus 5 cosine squared t. And that's my unit tangent vector. Okay, so that's the part we've done so far. Let's go on to find our normal vector then. So how do I do that? What do I need still do to find the normal? Well, you know what? Well, in my notes, I've got this written down here. Never mind. I'll do that one more step. Let's find this at the point T that we're given, just so that it's done. So if we're doing this at the point T that we're given, it was T equals 0, wasn't it? Okay. Then if I were to plug this 0 in, what would I get on the first one? 0. Good. On the second one, I would get 3 on top, I think, right? And then what would I get on bottom? Yeah, square root of 9, right? Square root of 9, so it would be 3.
Oh.
Yeah, so I would actually get the unit vector. I would get the vector 0, 1.
Do we just assume it's coming out of square root is positive?
Yes, the square root's a principal square root, so the only time that you have to worry about the pluses or minuses of radicals like that is when you insert the radical into the equation or whatever that you're working with. Yeah, otherwise it is already understood to be the principal square root, which is the positive part. Okay, are we ready to find our normal, principal normal unit vector? I don't think I got that right. Principal unit normal vector. I think I put the words in the wrong order. All right, so let's take a look. We need to find then t prime of t, right? So we're going to go back up to this and do a derivative because that's going to be fun. It's going to be messy, isn't it? It really is. So if I do the derivative of this, I would do the denominator, 4 plus 5 cosine squared t, times the derivative of the numerator, which is negative 2 cosine t. I'm definitely going to run out of space. I think I'm going to have to go to the next screen. Let me do that. I need just bigger screens. That's what I need. Minus the numerator, which was negative 2 sine t, times the derivative of the denominator. So the derivative of the denominator would be 1/2. And then 4 plus 5 cosine squared t. We're running out of time, I'm sorry, guys. Times 10 cosine t sine t. I'm just going to assume that what I have in my notes is right at this point, and we'll just write it down. If you guys want to tell me later that I was wrong, I'm okay with that. And this will be divided by the same value in the denominator, but squared. So 4 plus 5 cosine squared t. And then the other half of that looks very similar, right? Square root of 4 plus 5 cosine squared t times negative 3 sine t minus 3 cosine t. You guys can go back and fill in all these details from the notes later, right? No problem. 1/2 4 plus 5 cosine squared t to the negative 1/2 times negative 10 cosine t sine t, all over the same denominator. 4 plus 5 cosine squared t. All right, the best news ever. You ready for it? When you evaluate this at 0, you actually get negative 2/3, 0. That's what you get. Obviously, the magnitude of that is what? What's the magnitude of that? 2/3. It is. So the unit normal vector at 0 would be this vector, negative 2/3, 0 over 2/3, which would be negative 1, 0.
We know you love us too much to give us something like that.
Well, I love you so much, I'm only giving you 5 homework problems. 6 homework problems. How's that? 3, 4, 8, 11, 14, and 17.